Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always, there's an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. If you do me a favor, step on inside here. Let's learn something about polynomial equations, not just with rational roots this time though. No, there's more than that. There are also irrational roots and complex roots, things that are possibly imaginary solutions as well. You'll get a bunch of these here. I think I have 16 problems to do. There are some things you're going to have to need to know beforehand. First thing is you're going to want a calculator of some sort, perhaps one where you can enter values into a table. I'll have a personal one here, and I'll have the one that I pop up every so often right here as well. So I'll have both of those ready for you. You're also going to need to just know in general how to do some of the following things. And I keep mentioning I want to put up some videos that support these things that I've done in the past here. But you want to be able to know how to simplify radicals for one thing. You want to know how to simplify radicals. Now, I'll be doing them here, but I won't be teaching them as much here. These are assuming you know how to do these, simplify radicals. You also want to know how to solve by, and then this is like 2, 3, and 4. Taking square roots in general. Sorry about the handwriting. It's a sign of things to come, perhaps. Completing the square and quadratic formula. Now, quadratic formula is something I'm going to do. Oh, and then also by factoring, but we've been doing factoring a bunch. These are ones where we're going to find other things to solve when we have to in these ways. If I can solve by factoring, I will not solve using any of these methods here. I'm going to use these when I need to find irrational or complex imaginary sets of solutions. So just be ready for some of these things here, or perhaps there's an I that's involved. If there's one thing that we do have to know, it's that I is the square root of -1 in that way. When an I pops up, it's because we're taking the square root of a negative somewhere. It's just kind of part of that process there. Simplifying radicals will be a result of something we're doing as well with that. If it is something with an irrational or imaginary set of solutions, I'll solve with any of these as needed. You'll always see me solve using the quadratic formula, I suppose, because it's a fail-safe version. It's something that you kind of can do each time. Taking square roots is only kind of used when you don't have a linear term involved, no x to the first power, but you have an x squared and constant. And completing the square is something where you end up solving taking square roots, where I'll be using it when I have a 1x squared and an even linear coefficient. You'll see what I mean with them, especially if you know how to do them. Let's go and get started here. Every single one of these in 1 through 16, we are finding all zeros. Zeros is another word for roots or solutions here. They could say x-intercepts as well, because x-intercepts are values of x when y equals 0. What we're going to do in all of these right here, and I'm going to start it right off the bat, is I'm going to set this thing equal to 0. I'm trying to solve for x here. Now, I would check to see if I could solve by factoring, and I can't. If I factor out an x here, x squared, I'd get x minus 1. If I factor out a -1 here, I get 5x plus 3. I don't have the same common factor there. So here I'm going to start by using what's called the rational root theorem. My previous video just showed that. And the rational root theorem takes these p's over q's, and I'm not going to probably list them all the time. But in these cases here, I'm going to divide factors of 3 by factors of 1. So plus or minus 1 and 3, all divided by 1, is plus or minus 3. I'm going to try these 4 values here. If this thing has any rational roots, it will exist within these right here. And I'm going to try and test some of them by hand to start off with here. They're very small and they're integers. F of 1, you get 1 minus 1 minus 5 minus 3. That is -8, which is not 0. I need to get 0 out from this. If you didn't watch my previous video, then it'll make sense what I'm doing here. -1 minus 1 is -2, plus 5 is 3, minus 3 is 0. So -1 is a root right here, which means I can then factor this guy right here to x plus 1. That's the root for -1 there. And what's the other guy? I have to now divide. I have to divide this guy here by x plus 1. -1's my root here, with 1, -1, -5, and -3. I'm using synthetic division. Once again, these are assumed that you've seen some of these things before from the previous video. This is kind of an expansion onto that, right? So that factors out to become x squared minus 2x minus 3. X squared minus 2x minus 3. So I factor out an x plus 1, and then I have this as well. I need to find all my zeros. Now, in the form of a zero product property case, which will show up quite a bit here, if something times another thing equals 0, either that thing equals 0, which I could jump into, or that thing equals 0 right there. What I'm going to do is I'm going to still completely factor a little bit more. This is actually factorable straight up right here. And this factors into x minus 3 times, looks like another x plus 1 right there. So this has a x plus 1 kind of twice here, right? Another way of writing that is x plus 1 quantity squared. I'll show you that as well when it comes to the final solution set, so it makes sense what I'm writing ultimately. But again, zero product property. I'm multiplying 3 things to get 0, so one of them has to be 0. If x plus 1 equals 0, then x equals negative 1. If x minus 3 equals 0, then x equals 3. Now there's another x equals negative 1 right here, and do you have to write it twice? No, but I do want to bring it up in this case right here and what you should indicate. When it comes to us graphing and what we're going to do with polynomials down the line, it'll actually be very important. You can tell that x equals negative 1 does appear twice, right there and right there. This is what is known as a multiplicity of 2. This has a multiplicity of 2. The solution appears twice in that regard there. So when you see something like this when it's squared or when you factor into that form right there, that's what that means. So there are only 2 solutions. You know what? I should mention something else here, and I will in a second. Probably after finishing this problem. I should have started with it, really. There are only 2 solutions here, even though it's a cubic, and that's because one of the solutions did appear twice. Now, the thing that I should have mentioned from the beginning is one big understanding you're going to want to know about this whole thing is known as the rational root theorem. Excuse me, not the rational root theorem, excuse me, the fundamental theorem of algebra. I just did the rational root theorem. The fundamental theorem of algebra. So this is a big talk here. I'm going to say it very shortly. If you Google it, it might give you some mathy definitions, maybe something closer to what I'm saying here. But the fundamental theorem of algebra, it seems pretty important, right? Seems like good groundwork for algebra. The fundamental theorem of algebra states that in any polynomial, which all of these things are, the degree of the polynomial will represent the number of roots in the polynomial. They may be rational, they may be irrational, they may be complex, they may have multiplicities, but there will be that many roots. This was a cubic right here. I expect 3 solutions. I did have 3. 1, 2, 3. Now, one of them had a multiplicity of 2, which will appear. That's a part of it right there. So there are technically 2 solutions, one with a multiplicity of 2. Anyway, what you're going to notice in this fundamental theorem of algebra here is that in every problem that we do, we should get exactly that many solutions. And if you got less or you got more, something went wrong there. Generally, you would have more, not less. So if that does, generally you'd have less, not more by accident. Maybe you forget what's called a conjugate, which we'll run into a lot of those whenever we have complex and irrational solutions. Maybe accidentally forget to put some plus or minuses in that regard, or the multiplicity aspect. But I'll try and confirm each time. This was a cubic, I expect 3 solutions. Number 2 is a cubic. I expect 3 roots, 3 solutions in this one as well. So let's move on forward. Now, number 1, let me just mention this here. Number 1, you might look at this and go, Mr. Robinson, you just did a video doing this stuff before. How is this different? And I can't remember if I solved for you. I think all I did was factor. So now I'm actually solving in these things. Okay, that's not much different. Mr. Robinson, you've done that before. How is this different? How is this section different from others? Well, to my knowledge, maybe there's at least another one, but don't get used to all rational solutions here. And rational doesn't just mean integers. You can also have fractions, 2/3 and things like that. Don't expect all rational solutions, because here's the thing. If I went into sorry. I know what I want to say. I'm trying to think of how I want to bring it up. I'm going to bring up the calculator here. No, I'm sorry. If you use the calculator and you do what we did before, where you type in the equation and then you search for your solutions. If I type in x cubed, I don't know variables. If I type in x cubed minus x squared minus 5x minus 3, we've learned this thing. By the way, I'm going to use this. I'm going to use this thing a lot more now. Where I plug in numbers to see what I get out. I think this other one had really small numbers, so it was all good. So I can try 1, that didn't work. -1 did work. 3 will not, 3 does work, -3 will not work. So your 2 rational solutions are -1 and 3. Now that doesn't fully answer our question, but we did find those solutions right there. It's like, Mr. Robinson, why don't we just use that thing to find them if they exist among these rational roots right here? Because not all of your roots will be rational, and some of them might have multiplicities. If the point was solving, sure, you found the 2. You don't know which one would have had a multiplicity of 2, of course, the -1. But also, these aren't going to be the only ones that exist. We do want to start with them, though, especially if we cannot factor completely on our own. So let's move on to number 2 and see what this one's about. This one is a cubic, but there is a common factor here. This time I can factor an x out. If I set this thing equal to 0, and I factor an x out, don't divide by x, but factor the x out, you get a quadratic inside here like this. Now it's possible, and it appears that this is, well, if they're both negative, maybe, no, it's not factorable. It's not factorable there. So let me just bring this up right here now. We factored this down. This is not factorable here. You know, if this was a -5, it would have been factorable, but it's not. It's not a -5, it's a +5. So if this times this equals 0, that either means that this equals 0, which is one of your solutions, 0 literally, if I plug in 0, I'm going to get 0 out, or this equals 0, 2x squared minus 9x plus 5 equals 0. Now in the previous problem, like I said, I factored my quadratic, and then I was able to keep going forward, zero product property. This one's not factorable. Again, if this were a minus, it would have been, but this one's not factorable. So how do we solve? Well, we have either the completing the square or quadratic formula. Now I don't want to use completing the square here because of this 2 and this 9 and things like that. I want to use quadratic formula for this one, and quadratic formula is if you have ax squared plus bx plus c equals 0, then we're going to use x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. There are two solutions within here, negative b plus the square root of b squared minus 4ac over 2a, and negative b minus the square root of b squared minus 4ac over 2a. They may be just irrational solutions or imaginary solutions, but if this is not factorable, then they are not rational solutions. And I didn't have to use the rational root theorem this time. I found one of them off the bat from a common factor, and the other one seemed to be either irrational or imaginary. I'm going to guess they're just irrational based on the numbers here. Now, b squared minus 4ac is something known as the discriminant right here. I'm going to just put disc for discriminant. I'm going to start with that right there. That's where most of the calculation is done. And it helps me kind of determine what my solution type is as well. So if I just start with a discriminant right here, I'm going to get b squared minus 4ac, which is negative 9 squared minus 4 times 2 times 5, which is 81 minus 80, which is 1. Is that factorable then? Hold on, 81 minus, oh, I'm sorry, minus 40. I was thinking 4 times, never mind. I was thinking 8 times 2 in my head. I was thinking of 4 squared. Minus 40, which is 41. Okay, so 41. So my discriminant's 41. So when I substitute this stuff in, it's going to be x equals negative b, the opposite of negative 9, plus or minus the square root of 41, all over 2a, 2 times 2, which is 9 plus or minus the square root of 41, all over 4. So those are two other answers there for x. X equals these two guys and then this guy right here. Those are my three solutions, finding all the zeros. Now notice, there was only one rational solution that was 0. These others were irrational, not imaginary, but 41's not a perfect square, therefore no irrational solutions. And I can't simplify that radical either, by the way. So how many solutions are there? There's 1 and 2 and 3. The plus root 41 over 4 and minus root 41 over 4. And if you use a calculator, you could approximate it. I'll tell you what, root 41 somewhere between 6 and 7. It's probably around 6.5. Let's pretend it's like 6. It's close to 6. So you got 9 plus 6 over 4. So 15/4-ish. And then 9 minus 6 over 4, about 3/4-ish. Those are those two numbers. That's what they are. And they're not exactly those numbers. They're about. Okay, so anyway, you can see that that's what's going to happen every so often here, right? We'll have some things that are not necessarily all rational solutions. And using the rational root theorem the whole way with the calculator won't deal you with what you need to do. We have to divide until we can get through where we need to go. Okay, we have 2x to the 4th minus x squared minus 3. Now this appears to be in quadratic form, even though it's not a quadratic equation. So maybe we can try and factor this thing down here. I'm hoping and I believe it will be factorable. But remember, one thing will have a 2x squared if so, and one will have an x squared like that. Minus 3 and plus 1, I think. If you take a look at this right here, that'd be, oh, excuse me, minus plus 3 and minus 1. No, I'm saying this wrong. Hold on. Minus 3 plus 1. How does that look? 2 minus 3. There we go. Okay, I was lost in my I was multiplying this by this for some reason in my head. Okay, so those are the two things right there, right? 2x squared minus 3 and x squared plus 1. Now, neither of these can factor down anymore, so what we can do is use the zero product property concept and say either this guy equals 0 or this guy equals 0. Now, there are two different ways that I would look to solving this here. I would either solve using square roots, which I'll start with, or I'll solve using the quadratic formula, which it's probably, well, actually on one of these, it's probably more important to consider doing so. By the way, I expect 4 solutions here, so it's important for me to talk about that too. If I add 3 to both sides here, and then divide both sides by 2, I get x squared equals 3 halves. Now that's just x squared right there. If I take the square root of both sides right here, I'm going to get, now this is the part you're going to have to remember as part of the solution set, plus or minus the square root of 3 over 2. Now I'm not done here. I'm not going to box this just yet. There's more I need to talk about here, because when I use quadratic formula, this is not the answer I'm going to get. I think I'm going to get plus or minus root 6 over 2. But you'll see where that comes from with what I do with this afterward. On this one here, if I subtract 1 from both sides, and then I take the square root of both sides here, notice you get square root of negative 1 literally right there. The square root of negative 1 is I. So x equals plus or minus I. Not the square root of I, but just I. There are 2 solutions right there. This one I'm going to dot, dot, dot. Let's wait for a little bit. I'll use quadratic formula on, how about just this one right here? I don't know. I might do it on both. Time is a factor on this thing. I'll decide kind of slowly through this. But if I use the quadratic formula on this thing here, we could alternatively say x equals, now here's your a, here's your c. The b value is 0. This is 2x squared plus 0x minus 3. So, excuse me, let me start with the discriminant. Let's start with the b squared minus 4ac. The discriminant is b squared, 0 squared, minus 4 times a times c, which is 0 plus 24, which is 24. So the discriminant's 24. Now you can take the square root of 24, not as a perfect square, but you can simplify its radical, which is one of those things I want to talk about. So x equals negative b, 0, right? Plus or minus the square root of 24 all over 2a. Now the square root of 24 breaks up to square root of 4 times square root of 6. And 2 times 2 is 4. And the square root of 4 is 2. So you get plus or minus 2 root 6 all over 4. Now the 2 over 4 can reduce here, and you get 1/2. And so this becomes plus or minus the square root of 6 all over 2. Now those are the 2 answers that I expect there. And that's kind of something that I mentioned with this guy right here. There's more I have to do with here because these should be matching answers. I took this guy right here. And I did quadratic formula on it to solve. And although if you use the calculator, root 3 over 2 all divided by 2, the square root of all of 3 over 2 is the same thing as root 6 just divided by 2 there. But this one's not simplified right here. And you want it to be simplified. You want everything to appear the same way you would in quadratic formula. That's why I said it's likely I'm going to do quadratic formula on several of these to kind of show you what the official appearance is and how we can translate these. Now, the difference with these and the problem with this right here is this one actually is technically root 3 over root 2, which means the denominator is irrational. We want to rationalize our denominator, multiply top and bottom by root 2. This is a part of simplifying radicals you'd have to know how to do. The square root of 2 times the square root of 2 is 2. And the square root of 3 times the square root of 2 is the square root of 6. So you get plus or minus square root of 6 all divided by 2. The other thing the quadratic formula is good for, and I think I won't do this one right here. I wanted to call attention to this right now, and I'll use quadratic formula more importantly when I feel I need to. The thing that quadratic formula always calls attention to is the plus or minus aspect. You take that square root, you might forget the plus or minus aspect. One thing to remind yourself is, of course, though, you should expect 4 solutions to this thing, and there were. There were 2 irrational solutions. 1, 2. There were 2 imaginary or complex solutions. 3, 4. Boom, boom. There were 4 solutions in this thing here, and that's what we expected. 4 solutions. Now you'll notice on these irrational and imaginary solutions, they always come in what are called conjugate pairs. As long as I have rational coefficients and a constant right here in my polynomial, all irrational and complex solutions should appear in conjugate pairs, positive and negative versions of the same thing. When you multiply them through their linear factorization, that's what gets them to cancel out. The same way that linear terms cancel out in a difference of 2 squares, that's the reason, kind of, and that's how that thing works. Now, number 4, let's keep moving forward as we're already 20 minutes into here. And, I promise to speed up over time, but it depends on the kinds of problems that we have, especially if I can solve by factoring, I will. Now, we have here 8x cubed plus 27 and set equal to 0. Now, I'm going to write this in red to say kind of avoid doing here. What could potentially be done is you could say, let's subtract 27 from both sides, and then divide both sides by 8, and then take the cube root of both sides right here, and the cube root of negative 27 equals negative 3, and the cube root of 8 is 2, and you get negative 3 over 2. Now, that's not to say that this is not an answer. Clearly, if I substitute negative 3 over 2 into here, everything should work out because I cube it. I should get negative 27 eighths, and it should clear up, and that's good. But you don't want to stop there, and I don't want to just do that with my solution set because this was a cubic. I expect 3 solutions. I didn't get 3 solutions right here. What went wrong was I didn't follow the fundamental theorem of algebra. And it's not that one of these is a plus or minus. The cube root of a negative is a negative. It's not imaginary. That was fine. But I'm missing some of my other solutions here. Now, normally in solutions, what you'd expect to see is for them to actually cross your graph. Whether rational or irrational, they would actually touch or cross your x-axis. But imaginary or complex solutions do not, and that's what this thing has here. 8x cubed plus 27 as a function does, something like this, whatever. But it only crosses here just once at negative 3 halves. Where's that other point? Where are the other 2 points? They're imaginary or complex. And this comes through needing to use rational root theorem, or if you understand that this is a sum of 2 cubes, you factor. And this thing factors into sum of 2 cubes, a cubed plus b cubed, right? A cubed plus b cubed is a plus b times a squared minus ab plus b squared. So this stuff, once again, when I do this stuff, I assume that you've done factoring sum and difference of 2 cubes and working this thing out. Now what you can see as I work this thing out here is, well, here was one of my solutions that we just saw before. If this equals 0, then x equals negative 3 halves. Okay, that's one of my solutions. But there's a whole nother set of solutions right here, which is 4x squared minus 6x plus 9 equals 0. Set that equal to 0 and solve. And you might want to look to factoring there for yourself. You might say, all right, maybe it's factorable there. If you remember my sum difference of 2 cubes video, I state specifically, or actually I don't know if I stated in that, but I did for my students in another thing. I stated specifically, this guy is never factorable. Not only is it never factorable, but these are imaginary or complex solutions. I'm going straight to quadratic formula on this one. Straight to quadratic formula. I'm not even attempting to factor this one. So let's go straight to quadratic formula here, where I do the discriminant as b squared minus 4ac. And here's the reason why this thing's always what I said it was. The discriminant on these is always negative. The b that gets squared is always smaller than the 4 times a times c portion of it. And because these things have to be squared right here, you're always subtracting from it. So that never changes. Anyway, it's 36 minus 144, which is negative 108. So that being negative means imaginary or complex solutions. It's going to have an I in it, and something with an I or irrational is never factorable. So straight up there. So let's keep going. Let's solve these things. Let's get x equals. So negative b, the opposite of negative 6 is 6, plus or minus the square root of 108, all divided by 2 times 4, which is 8, 2a, right there. Now we can, negative 108. Now we can simplify the square root of negative 108 right there. 12 and 9, 36 and 3. So this thing is 6 plus or minus root 36 times root 3, all divided by 8. You can see I'm only simplifying the radical right now, and it's still taking the most time out of the problem that I'm working on here. That's why, like I said, doing the discriminant first kind of helps, because those are 2 steps already that I'm saving from just writing the same part over and over right here. 6 plus or minus 6 root 3, all divided by 8 like that. So that would be the solution set right there, but these can all divide by 2. It's like if I factor out a 2 on top and then the 2 on bottom here, these turn into 3s, and that turns into a 4, and then we get 3 plus or minus 3 root 3 all over 4. Now simplifying reducing fractions is something that's important for you to need to know how to do in that regard there, and hopefully that kind of made sense what I sort of did there. So there were 3 solutions. Hold on, I'm trying to find. I'm going to talk as I'm saying this thing. There were 3 solutions there. There was the negative 3/2, and then there's that plus or minus there with the, oh, I didn't mention I. I'm sorry. I was so focused on the 108, I didn't ever consider the fact that there's the I there. There we go. Good thing I'm not talking over what I'm trying to write. So the I there. So there's 1 real solution in rational and 2 complex or imaginary solutions there with the I. Square root of a negative brings out the I in the best of us. Okay. So there it is. There's the first 4. We're 25 minutes down here. Now these problems might get a little bigger right here, but we'll see what we can do. Number 5. Now in this one right here, I'm immediately looking to factoring by grouping. There are 6 terms, and I think I've mentioned a couple times if I know what I can factor by grouping. If the coefficients fall in proportion with each other, notice how this is always 5 times that, this is 5 times that, this is 5 times that. And based on the degrees there, you can factor by grouping. It's going to be a little different since it's 6 terms, but if I factor out a 3x to the 4th in the first guy, I'm left with an x plus 5. And if I factor out an 11x squared here, I'm left with an x plus 5. And here, if I factor out a 6, I'm left with an x plus 5. So set this equal to 0, excuse me. So x plus 5 is a common factor in all 3 sets here. So if I factor out the x plus 5 here, then here I'm left with 3x to the 4th plus 11x squared plus 6. That's all set equal to 0. So this guy's clearly one of your sets right here. Maybe this can factor down more. I'm looking at it, the 2, 3. Yes, so this can factor down more here. This factors down to a 3x squared plus and an x squared plus right here, where this is, what was I going to say, a 3 and a 2 right there. 9 plus 2 is 11. 2 times 3 is 6. So it factors down to like that. So I'm probably not going to use quadratic formula on this one. I think these are straight up solving using square roots. Pretty simple there. I haven't seen a complete and square one yet. But if x plus 5 equals 0 here, then we know that that solution set, or that solution here should be x equals negative 5. By the way, I expect 5 solutions in this one right here, 5th power. This one here, if 3x squared plus 2 equals 0, subtract 2, divide by 3, and take the square root of both sides. I said I'd always use quadratic formula. Now I don't know whether I should or not. It adds time to the video. And I think I want to mention what's most convenient for you if you can use it. With the negative here, so there's going to be plus or minus to start with. There is an I. And here's that root 2 over root 3. Now you might wonder where the negative went. Well, there's the plus or minus, but the negative has to do with the I. It's not a negative number. It's an imaginary number. It's negative inside the square root. Now if I rationalize the denominator by multiplying top and bottom by root 3 here, I'm going to get root 6 over 3, or I root 6 over 3. So plus or minus I root 6 over 3. Those are 2 answers right there. The last 2, x squared plus 3 equals 0. Let's subtract 3 and take the square root of both sides. Whoops. Speaking ahead of myself. Whoops. Thinking ahead of myself. Negative 3, take the square root of both sides. And it's just I root 3, plus or minus I root 3. Plus or minus I. That's a blend between an I and a square root here. Plus or minus I root 3. Okay, 5 answers there. 1 real rational integer. 4 complex, 2 pairs of complex conjugates right here. I root 6 over 3, negative I root 6 over 3. I root 3, negative I root 3. Those are the other ones. So if factorable, it kind of makes things easier there. And factoring by grouping really helped as well. I saved myself from searching for negative 5 in my rational root theorem. Because in rational root theorem, what would have I had to have done? I would have had to test my p's over q's here. I'm not going to do it all, but I would have had to test p's over q's. Now I would have done factors of 30 as plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. All divided by factors of plus or minus 1 and 3. So positive 1, negative 1, positive 2, negative 2, positive 3, negative 3, positive 5, negative 5. I would have tested 8 before I landed on just negative 5. Negative 5 is the only rational value in these. All the other ones don't apply. The other ones are complex imaginaries right there. Irrationals, even, if you will. All right, number 6. Looks like I could maybe factor by grouping again. It looks like this is always 5 halves times more, if you will. So I'm going to begin by factoring by grouping here, see what we can do. If I factor out a 5x to the 4th on the first guy, I have 5x plus 2. If I factor out a negative, remember, got to get that negative out there. It looks like 2x squared. I also get what looks like 5x plus 2. And then a negative 7 here, I get 5x plus 2. So equals 0. 5x plus 2 is one of the factors there. The other one is one of those quartic guys again. 5x to the 4th in quadratic form, excuse me, minus 2x squared. My side kind of twitched strangely. Equals 0 there. Yeah, sorry. Yeah, this is factorable. All right. So this guy here, 5x plus 2, and then I have a 5x squared here, and here I have an x squared with positive 1 and negative 7. So 5 minus 7 is negative 2 right there. That equals 0. So looks a lot like the previous one, only one of my sets will just be irrational, not imaginary or complex. So 5x plus 2 equals 0. 5x equals negative 2. X equals negative 2/5. There's my one rational solution. And if you used the rational root theorem right there, negative 2/5 is the only one that would have worked out. So I would be testing a lot of values in my calculator before I find negative 2/5, use synthetic division on it, and then you're down to this guy right here. And then you can either use rational root theorem again. Can't really use quadratic formula unless you use an x squared equals kind of thing. And you can do that. Just take the square root of both sides. Still got a rationalized denominator. So in this case here, I'll just solve using square roots. 5x squared minus 7 equals 0. I regret having said I'd use quadratic formula over and over. And these guys here, I don't plan on doing it. I want you to know how to rationalize denominators on its own. You would have to with quadratic formula given what you have here anyway. So x squared equals 7/5, and if you take the square root of both sides, you get plus or minus root 7 over root 5. And if you rationalize that by multiplying top and bottom by root 5 there, you get root 35 over 5, plus or minus root 35 over 5. So those are irrational, but they are real. And no, root 35 over 5 does not become root 7 or anything like that. You can only divide things, irrationals with irrationals and rationals with rationals there. This other one here does have imaginary or complex solutions. X squared plus 1 equals 0. X squared equals negative 1. Take the square root of both sides. You get plus or minus square root of negative 1 or plus or minus I. We've seen that before, and there they are. So 5 solutions again. 1, 2, 3, 4, 5. 2 complex that are conjugates, 2 irrationals that are conjugates, 1 rational there. So once again, only solvable in that form. Number 7, quartic and quadratic form straight up. Hopefully this is factorable in the way the other ones were. I'm going to go and test that out right now. I'm going to try 5x squared with an x squared. And equals 0. This is a plus and plus format. With odd numbers here, I'm going to try something like 8 and 3 or 24 and 1. I'm going to start with the 8 and 3, and I just found it in my head. Here's 3, here's 8. That's 15 plus 8, which is 23. So set these equal to 0 here. It's kind of easier problem compared to the other two because of what we had to do here. So 5x squared plus 8 equals 0, or x squared plus 3 equals 0. Let's start with this one here. Subtract 3. Take the square root of both sides. You get plus or minus I root 3. Whoops. All these look like they'll be imaginary or complex solutions here. Subtract 8. Divide by 5. Take the square root of both sides. Plus or minus I root 8 over root 5. Now, a couple things have to happen here. There is the rationalizing the denominator, but root 8 turns into root 4 times root 2. So that's 2 root 2. 2I root 2 over root 5. So now I got to multiply top and bottom by this root 5 right here to simplify. And we will get plus or minus 2I root 10 over 5 right there. So plus or minus 2I root 10 over 5 plus or minus I root 3. Now, given those, that is 4 solutions, all imaginary, complex right there. I's plus minus, it was a quartic. We're all good to go. All right, number 8. Excuse me. X cubed plus 125. This goes back to kind of what I mentioned before with the sum difference of 2 cubes kind of thing. Excuse me. I need to get a drink of water here. This is a sum of 2 cubes. And being a sum of 2 cubes right here, there's not just one solution. It's not just negative 5, which would work here. This is, if I cube x, I get x cubed. If I cube 5, I get 125. So this is going to be your a plus b. And then you get a squared minus ab plus b squared. Right there. So negative 5 is a solution. But the other one, you set this equal to 0. Once again, quadratic formula, or completing the square. So completing the square hasn't surfaced in a way that I'd want to do it. This is a 1x squared. That does help. But, because remember, this is not factorable. But this is not an even number. It's in completing the square, you divide this by 2 and square it. I don't want to deal with fractions outside of what the quadratic formula already gives me as a fraction, because I don't need to find a common denominator. So I'm going to use quadratic formula straight up here. Let's start with the discriminant. So we'll go b squared. And remember, we expect a negative discriminant here, right? B squared minus 4ac equals 25 minus 100, which is negative 75. Now, before I go further on quadratic formula, let's already work out the square root right here. This will be I root 25 times root 3, or 5I root 3. That's that square root of b squared minus 4ac portion, not just the b squared minus 4ac portion. So let's keep going. That's going to be x equals negative b, that's 5. Opposite of negative 5 is 5. Plus or minus, here we go, square root of b squared minus 4ac, all over 2 times 1, all over 2a. Boom. Right there. And that's your other solution. So those are your two solutions right there. You can see how much time I saved in quadratic formula by working some mental math here and there, simplifying that radical, things like that. And, there's a truth to simplifying the radicals here when it comes to the imaginary versions of this form. It always takes on this one appearance, nothing to memorize but compute. But it is there. Those are your other two solutions, and we're all good to go in that cubic. All right. So, I am probably going a little faster now, right? That was only like 12 more minutes added onto the first 4 problems that I did. And you can see where I'm speeding up. I got 8 more problems to do. I expect to finish definitely within the hour, I believe, unless rational root theorem really takes its toll. I think I see rational root theorem right here. But, a lot of this stuff now in a video like this assumes that you've done some of these things before. Quadratic formula, completing the square, which you haven't run into yet. Sum of 2 cubes, difference of 2 cubes, simplifying radicals. Like I said, entering this video, expecting you know how to work some of this stuff out. And I'm talking through it. Maybe you're learning as you go, but that'll help. Anyway, I can't factor by grouping this time because this number's, if this was a 60, if this was that, yeah, I could factor by grouping. No, I can't here. So I'm going to use rational root theorem this time. Let's try some of our p's over q's. Our p's over q's right here, we're going to do factors of 6. I'll divide by factors of 1, by the way. So 1, 2, 3, and 6. And let's test these in here. I'm going to go to the calculator this time just to kind of give you the old college try. Let me first write this out for you. X cubed plus 3x squared minus 20x plus 6. Okay, so you can see the 8 things I'm going to try. And I'm going to test this until I find one that actually gets me a 0. So here we go. So I put in this equation right here. Okay. I'm going to go to my table, and I'm going to try positive 1, negative 1. So 1, negative 1. Let's try positive 2, negative 2. 2, negative 2. Try positive 3, negative 3. Okay, 3 is one of them. Boom, right there. And for all we know, it might be the only one. This is a cubic. We expect 3 solutions. But unless here, let me go through the other ones anyway. Let's see if they are. 3 and 6 and negative 6. Nope, there's only one of them. So just the 3. It's the only rational solution. The others are either irrational or imaginary or complex, right? So that means don't expect the next part to be factorable. And even if you did find those other things right there, we've spoken on multiplicities and things like that, I expect us to still factor the rest of the way. So here we go. This factors into, what did I say it was 3? So this factors into x minus 3 times, oh, I got to divide, I'm sorry. 3 is my root, so this will be 1, 3, negative 20, and 6. So the 0 remainder, we get 1x squared. That definitely does not look factorable. 1x squared plus 6x minus 2 equals 0, like that. So this is what it factors down to. Looks like 3 is going to be a solution, right? X equals 3, one of our solutions. And let's take a look at this one right here. If x squared plus 6x minus 2 equals 0, I can use completing the square this time, and I intend to do that as one of my ways. I'll still use quadratic formula for you guys, but we'll see what else we can get out of this. So if I use completing the square here, completing the square, I'm going to add the 2 over to this side, and I'm going to add something specific right here and right here that'll give me a perfect square trinomial. 6 divided by 2 is 3, and 3 squared is 9. That gives me a perfect square trinomial because the two numbers that multiply to 9 and add to 6 are 3 and 3. That's what we want. We want some sort of boom guy like that. And 2 plus 9 is 11. So now we have something that factored down to a perfect square there, where I can now take the square root of both sides, and I get x plus 3 equals, whoops, I don't need the parentheses. I get x plus 3 equals plus or minus the square root of 11. If I subtract 3 from both sides, I get negative 3 plus or minus the square root of 11. Now, I prefer completing the square in a problem like that. I believe it's shorter than quadratic formula. Furthermore, I won't have to do a fraction reduction on it. So there's a completing the square version. And you see what I had here. As long as that's a 1x squared, I can take this divide by 2 and square it, and I get this number that we add to both sides. So I can now factor down to this stage right here. I can then take the square root. That works out. I can't solve using square roots because I have the linear term until I get it into a 1 perfect square factored thing. So let's try quadratic formula on that as well. Here we go. If I did quadratic formula on the same guy up here, the discriminant is b squared minus 4ac, which is 36, plus 8, which is 44. Now, we've spoken on simplifying the radical beforehand if we can. That's root 4 times root 11, or 2 root 11. So this is now the square root of b squared minus 4ac. So let's try and clean that up. Negative b plus or minus the square root of b squared minus 4ac all over 2 times 1, 2a. Now you divide those all by 2, and you get what we were looking at here before, which is negative 3 plus or minus the square root of 11. Still not too long. The numbers were relatively small there. In fact, you can argue that's less writing than what this was here. I'd say these steps are a little bit easier to work with. Remember, I did have to simplify that radical. I did have to recognize here that I'm doing that, and I probably skipped some steps in between. I work a little fast on quadratic formula or completing the square, but it's all good. I'm a fan of anything that's very useful for the problem. But it was a cubic. I got 3 solutions, 3 and negative 3 plus or minus root 11. Once again, a conjugate pair for irrational solutions. Okay, number 10. Cannot factor by grouping here. But there's a common factor to start with. If I factor on x squared, I'm left with x cubed minus 3x squared minus 26x minus 24. I still can't factor by grouping, but one set of solutions, this is x to the 5th, I should have 5 of them. One set of solutions is x equals 0. Now you notice, it's really x squared equals 0, therefore x equals 0. That's one solution, but it has a multiplicity of 2. And I mentioned before how that kind of works. Because it's squared, it's really x times x. There are 2 instances where I could have substituted 0 to make the whole thing work, and it does change things when we talk about graphs some other day here. So, rational root theorem right here on this guy, when this is set equal to 0, x cubed minus 3x squared minus 26x minus 24. Let's go to rational root theorem here, and let's do our p's over q's. Those are factors of 24 over factors of 1. So plus or minus 1, 2, 3, 4. I'm going to just go until I find one of them. 6, 8, 12, and 24. Now, a good question could be asked. What if none of these were rational solutions? I'll be honest. I'd probably have to give up in some way. I'd have to know what one of the other what one of the irrational or imaginary solutions are, use synthetic division on that and play with it. I'd kind of have to surrender at that point for myself unless I was given what one of the roots or things was and work with complex things. But here's the thing. As long as it's a cubic, one of them has to be rational, because what I mentioned was as long as these are rational numbers here, imaginary, complex, or irrational solutions have to come in conjugate pairs, a plus or minus. So even if 2 of them are complex or irrational in the plus or minus, boom, boom, there's only one solution left. Only one solution left, which means it can't be an irrational or a complex one because they have to come in conjugate pairs. So one of these has to be rational. One of them, at least one of them, has to be here. It has to. It has to. So, and it could be -1 when I can't tell. Actually, you know what? Maybe it's not -1. I can't tell. I was trying to do it mentally. Let me enter this in my calculator and go from there. So x cubed minus 3x squared minus 26x minus 24. All right. You know what? Just trust me on this when it comes to me entering values, if that's okay. I see -3 is one of them, but I'm going to go for a smaller one just because that's how I'll naturally do it. 1, -1, 2, -2, 3, -3. Okay, -3 is the first one that I run into. It might be the only one. It could be among these as well. So -3 is one of them. So f of -3 is 0. So let's go ahead and do rational. I keep messing up my terms tonight. I'm sorry. -3 is my root here. So let's use synthetic division on this 1, -3, -26, and -24. We're going to get 1, -3 is -6, 18, add that's -8, add that 24, you get 0. So here we go. That looks non-factorable. So this does break down into, here, you know what? I'm going to keep the things that were up there as well. I'm going to rewrite that x equals 0 down here again. So x squared was one guy. X plus 3, with -3 being the root, is 1. And then x squared minus 6x minus 8 is the other, like that. So once again, what I mentioned here before was x equals 0. That's a multiplicity of 2. X equals -3 is one of them right here. And there's a pair right here that'll work. This isn't factorable, though, so we're either going to use quadratic formula or completing the square. I'll try and fit both as I can right here. For completing the square version, I would say x squared minus 6x plus something equals 8 plus something. -6 divided by 2 is -3. Square that is 9. So we add 9 and 9 again. We talked about that before. This is x minus 3 quantity squared here equals 17. You take the square root of both sides. X minus 3 is plus or minus the square root of 17. Add 3 to both sides. X equals 3 plus or minus the square root of 17. Quadratic formula, I can't really fit. I mean, I can. I'll squeeze it in somehow. Let's try and bring some things up here. I tried to give a lot of room for these problems, but you know, you do what you can. The discriminant, let's start with there. Discriminant, we'll get b squared minus 4ac, which is 36 plus 32, which is 68. 68 is a square root. Breaks down into root 4 times root 17, right? Yeah, which is 2 root 17. So x equals -b, opposite of -6 is 6, plus or minus square root of b squared minus 4ac, all over 2 times 1. Boom. Divide those all by 2, you get 3 plus or minus root 17. Sorry, very short on room there. So those are your 5 answers. 1, 2, right? Multiplicity of 2, 3, and 4, 5, because the plus or minus there are 2 different answers in a fifth power, in a quintic. All right, that problem took a little bit more time here. I still should finish within the hour, I think. I don't know how big the problems get here. Not another factoring by grouping, but there is, once again, another common factor here. There's a common factor of x, and I get 2x cubed plus 3x squared minus 43x minus 40 equals 0. I can't guarantee I'm going to finish within the hour because I don't know how deep these problems get. If they're all rational root theorem, then, you know, there's not much I can say about that. So x equals 0 is one of my solutions, right? Not a multiplicity of 2 this time, just that right there. And let's go on rational root theorem here. List some p's over q's, and we get plus or minus all factors of 40, 1, 2, 4, 5, 8, 10, 20, and 40, all divided by factors of 2, 1, and 2, which is plus or minus those 1, 2, 4, 5. Now, I don't think I'll finish within the hour. 8, 10, 20, 40, and then divide those numbers by 2, you get 1/2. 2 over 2 is 1, we already have that. 4 over 2 is 2, we already have that. 5 halves. Basically, I think here I'm just running into the odds. Like, 8 halves is 4, 10 halves is 5, 20 halves is 10, 40 halves. Yeah, so that's it. So those are the only ones right there. That's a significant amount. That's 20 different things to test. So 1 clearly doesn't work, but I'm going to enter this into my calculator again. Let me show you what I'm going to type here. Type 2x cubed, 2x cubed plus 3x squared minus 43x minus 40. And let's try some numbers here. None of those work, apparently. So 1, -1, 2, -2 didn't work. 1, -1, 2, -2. Let's try 4 and -4. Nope. 5, -5. Good thing I'm testing in here. 8 and -8. 10 and -10. Honestly, as the numbers get bigger, I'm less and less inclined to believe it'll be these. It's probably one of the fractions. 20, -20. But it has to be one of them. Because once again, being a cubic, I need at least one rational solution in this thing. 40 and -40. At some point, I give up and say, those are too big. So let's try 1/2 or -1/2. And then 5 halves or -5 halves. Has to be one of these. 5 halves, -5 halves. I must have done something wrong. Let me make sure I type my equation correctly here. 2x cubed. Oh, that wasn't 3x squared. I did 3x too. See? Here's the thing. I know one of those has to work there. So anyway, let's try these again. Sorry about that. 8, -8. At least you're watching me do it instead of just doing it on your own. 10, -10. You know, as these numbers get bigger, hold on. I'm going to try the fractions first. 1/2, -1/2, 5 halves, -5 halves. Something's going wrong here. Let me pause this and see what's going on. Okay, I think I cracked what it was. I haven't tried it yet, though. I didn't try 5 and -5. I don't know if I skipped it the first time. I think I went straight from 4 to 8. So let me try those. 5, -5. There it is. Okay, there were kind of two issues in one there. So -5 was it right there. Okay, I kept looking through my list, and I'm like, what's going on? And then I skipped 5 and -5. I might have got it right. I might have not skipped it the first time, but I wrote it as 3x2 instead of 3x squared the first time. So what I say was -5. So f of -5 is 0. Anyway, you can see that it takes a while to test either way there, but a little mistake. All right, synthetic division on this guy right here. Let's see what it also factors down to. I get a 2, a 3, a -43, and a -40. And there we get, and that's what happens when you record this thing live. -10, -7, 35, -8, and 40, and 0. But here's the thing. One of the rational solutions has to work. It always does. It just does. So the whole thing, I remember x equals 0 is one of them, but I'm going to bring it down here. X plus 5 is a factor with -5 is the root. And then 2x squared minus 7x minus 8 is the other guy there, equals 0. Does that factor? I don't think so. Let me try it. You know what I can test? I'm going to test the discriminant here. I don't think it does, but I'm going to test the discriminant here. And if this is not a perfect square, then that means it's not factorable, which means quadratic formula is something I would have done anyway. B squared minus 4ac. That's a -8, which is 49 plus 8 times 8, 64, which is 113. Definitely not a perfect square, so this is not factorable. If this was a... There are a couple numbers that this could have been for it to be factorable, but not this. If it was -17, I think it would have... maybe -15, I think it would have been factorable. All right, so anyway, as far as two solutions go, we mentioned x equals 0 as one of them, and x equals -5 we also found as one of them. So the rest is in the... is this a quartic? The rest in this quartic, the last two, are irrational because it is a positive non-perfect square right there. So square root of 113, I think it's a prime number as well that I can't simplify. So let's figure it out. X equals -b, opposite of -7, plus or minus the square root of b squared minus 4ac, all over 2 times 2. 2a is 4. Those are the other two. Quadratic formula is just like, that's all it was. I'd use the discriminant portion. I used it to test, and then I just wrote out those last two answers, and that's it. That's kind of nice. All right. Yeah, definitely not going to finish on time here. That was just number 11. Number 12 can go pretty fast, though. I'm already seeing a sum of two cubes, and hopefully you can see the same thing as well. 27x cubed plus 64 equals 0. We're cubing 3x right there, and we're cubing 4 right here. So now we got 3x squared minus 3x times 4 plus 4 squared. So in one solution set here, 3x plus 4 equals 0. 3x equals -4. and x equals negative 4/3. Here on out, if I have something like that, I'm just going to write negative 4/3 straight up. I'll say subtract 4, divide by 3, and hopefully you'll kind of know what's going on with that. The other two solutions, like I said, quadratic formula is really my go-to on this one here. So let's start with the discriminant portion, as that's not factorable, remember. It's b squared minus 4ac, which is 144 minus, go to the calculator, 64 times 9, 576, I think, which is 432, negative 432. Boy, pretty big number there that I'm giving you guys, but you know what? It's a part of it. Let me make sure of that. 144 minus 576. Yeah, negative 432. Okay, so negative 432. Now, you can bet that that's something you can take the square root of, because it definitely has a 4 it can divide by. That's among things. It's possible that, oh, you know what? Actually, the way that this thing tends to work here is this is 3 times that of 144. And 144, as we know, is 12 squared. So, again, there's a thing to that that does kind of help you out. But it's I times root 144 times root 3, which is 12 root 3, 12I root 3. So, as long as you can simplify the radical, break it down, and find things that'll help you out, that's the largest perfect square you can take out of it. So, let's see if we can do this kind of all in one step the rest of the way besides reducing the fraction. X equals negative b, so 12 plus or minus this 12I root 3 all over 2a. 2 times 9 is 18. So that's going to be x equals, if I divide everything by 6, I get 2 plus or minus 2I root 3 all over 3. And there must be more patterns than this that I'm aware of here. If you notice that 2 plus or minus 2I root 3 over 3, where'd I have another one? It was with the 5s, right? 5 plus or minus 5I root 3 over 2. I thought they were over 3 as well. Anyway, so yeah, there are some patterns within that I'm sure that you can play with there. I'm not positive on all of them. All right, 4 more problems to go. I'm about to pass the hour mark in a few minutes. I see factoring by grouping. I'm going to attack it right now. Let's go. All pluses. You can see these are 5 times larger than the thing before it. So I can factor out a 5x to the 4th. And here I have x plus 5. And then I can factor out an 8x squared, and I have x plus 5. And here I can factor out a 3, and I have an x plus 5. Okay, so that's x plus 5 times 5x to the 4th plus 8x squared plus 3. Does that not look like one we did before? Did we have one with 5x to the 4th, 8x, and 5x? You know, I want different kinds of problems. Let me see if we had that kind of problem before. Maybe not. No, we had ones with 5. Oh, that was a different set of numbers. Okay, different set of numbers. I feel a little better then. I want them to be different. All right, let's see here. It does factor, though. So x plus 5. So this is 5x squared here, and x squared here. And plus plus, that's going to be plus 1 and plus 3. 5 plus 3 is 8. So let's see if we can work these things out here. If x plus 5 is 0, then x is negative 5. I think we've seen this one a couple times. You know, subtract 1, take the square root, you get plus or minus I. We've seen that a couple times there. This one right here has some work to do. How about this? X squared subtract 3 divided by 5, you get negative 3/5. Now we take the square root of both sides. It's plus or minus I root 3 over root 5, right? Take the square root of top and bottom. And then rationalize that denominator. Root 5 over root 5. And that'll give you plus or minus I root 15 all over 5 like that. So fifth power, 1, 2, 3, 4, 5 solutions. Only one real, rational integer. The rest complex, imaginary solutions. Conjugates. All right, quartic business right here. Let's hope it's factorable. That's the whole goal of these when they have this quartic form. So let's hope we get something of that accord here. I'm guessing a 3, whoops, set this equal to 0. I'm guessing we get a 3x squared somewhere. I'm going to try 7 and 8 as my first two guys to deal with here. 7, yeah, right here. 7 minus 7 plus 8 would give you negative 21 plus 8 is negative 13. So that's good. All right, we're nearly there. Let's start with this one here. This is a little bit easier. X squared equals 7 when you add 7 over. And take the square root of both sides. You get x equals plus or minus root 7 right there. Two solutions. Right here, we're going to get some imaginaries going. We get 3x squared equals negative 8. X squared equals negative 8 thirds. Take the square root of both sides. Plus or minus I root 8 over root 3. Before I rationalize the denominator, please recognize that root 8 is root 4 times root 2, or 2 root 2. So 2I root 2, plus or minus 2I root 2 over root 3. Now I multiply top and bottom by root 3, and that's going to get a root 6 here. So 2I root 6 over 3. Again, rationalizing, multiply top and bottom by that root. So those are the two right there, and these two right there, and that is our quartic. Quartic, 4 answers. 2 more problems to go. Number 15. Already looking at common factor things that we want to play with here. Negative 8x to the fourth plus x. I can factor a negative x out, and I'm left with 8x cubed plus 1. Now this gives me one of my solutions. X equals 0 is one of them right there. Don't worry about the negative. It's just a negative 1. It's not really a part of it. This guy right here looks like a sum of 2 cubes. So this is going to be, if 8x cubed plus 1 equals 0. Here we're cubing 2x, and here we're cubing 1. Then 2x quantity squared is 4x squared minus 2x times 1 plus 1 squared, and that equals 0. Whoops. Oh, I'm sorry. Hold on a second. This is a minus 1. It's still a thing of 2 cubes, but it's a minus. Let me do that again. Minus 1, minus 1, minus 1 plus 2x. Let's do that again. Difference of 2 cubes because I factored the negative out. Got it. Okay. So, anyway, add 1 divided by 2, x equals 1/2 is another solution right there. As a quartic, I expect one more solution. Here's 1, here's 2, here are 2 more. Quadratic formula, start with the discriminant. So we're going to go b squared minus 4ac, which is 4 minus 16, which is negative 12. When I take the square root of the negative 12 there, that's I times root 4 times root 3, so 2I root 3. So that's going to be part of the plus or minus portion there. So we're going to get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. 2 times 4 is 8. I guess the way that the top works is it's always negative b plus or minus bi root 3. It looks like that's always appearing. There's probably something to it that I could figure out with you as a pattern, but again, practicing discriminant and such, it's probably worth doing what I do. Divide everything by 2 there. You get x equals negative 1 plus or minus 1I root 3 all over 4. So those are the other two answers right there. So 1, 2, 3, 4 answers there. Fundamental theorem of algebra taking hold. And one more problem as we are past the hour mark. One more problem here. Probably because I spent time not looking for 5 and negative 5 in rational root theorem that one time. This does look like factoring by grouping here. Lots and lots and lots of factoring by grouping. Where you can factor out a 2x to the fourth, and I get 3x minus 1. And then I factor out an 11x squared, and I get 3x minus 1. And I factor out a 9, and I get 3x minus 1. As 3 is a common factor here, or 3x minus 1 is a common factor here. The other guy is 2x to the fourth plus 11x squared plus 9. Let's try and factor that. Otherwise, it's no fun. Rational root theorem we'd have to do. 2x squared here and x squared here. Both pluses. Yeah, definitely. 1 and 9, right? 2 plus 9 is 11. Okay. So add 1 divided by 3, you get 1/3. Here, subtract 9 and divide by 2, you get that guy. We'll take that square root in a second. Subtract, we've done this a lot. Subtract 1, take the square root, you get plus or minus I. Square root of negative 1. All right, last two to do right here. Take the square root of both sides, you get plus or minus I. Square root of 9 is 3. Let me write that right now. Plus or minus 3I. Plus or minus 3i over the square root of 2. And when you rationalize that, multiply top and bottom by root 2, it's plus or minus 3I root 2 all over 2, like that. And that should be the last one, the last guy right there. Okay, so did I say 1/3? Yeah, 1/3 I plus minus 3I root 2 over 2. That is 5 solutions there. So what you're looking at right there, we did a bunch of different things, guys. We practiced factoring normally, factoring by grouping, factoring quadratic form, factoring sums and differences of two cubes, no sums or differences of two squares. We did rational root theorem, in greatest common factors. We did rational root theorem. We used zero product property, quadratic formula, completing the square, solving using square roots, and rationalizing the denominator, all within about an hour's time there. 16 problems, a lot of things to do, guys, and they can get a little complicated. You can see why rational root theorem can't just be, and multiplicities. So we can't just say, just plug in all the numbers and write them out, and then we have them all the answers. No, there are a lot that are irrational. There are some with multiplicities. If you don't get the common factors out with the x equals zeros first, that can take form. And then you got to find them using quadratic formula or completing the square right there. So that'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. And next time you see me, we're probably doing a bit of a mixed review with everything involved, which is just you assume nothing when it comes to these problems. Some are just straight up factoring. Some are solved little quadratics. Some are a difference of two squares, special cases, and perfect square trinomials. And then some just get big and monstrous. And you just do what we do with these when it comes to factoring them. But that ought to do it, guys. This is Mr. Robinson. Thank you so much for watching. And I will see you in the next one.